So in this video, we're going to look at a visualization of hydrogen atom orbitals. And so you're familiar with this notation already, but just to reemphasize, and I've been using it, we labeled hydrogen atom orbitals with different L quantum numbers with different letter labels. So L is equal to 0 is what we call an s orbital. L is equal to 1, we call a p orbital. L equal to 2, we call a d orbital. And L equal to 3, we call an f orbital. And in this image I'm showing you, we're only looking at a particular one of these, right? So for example, and the quantum number here on the right-hand side, these are the n values. So this is n equals 1, 2, 3, and 4. So for example, if we look at this p orbital, the 2p orbital, there are actually 3 of these with different m values. We have m equals -1, 0, and +1. And this is just showing one of those orbitals. And so there's some trends there. So when we looked briefly at the wave functions in the last video, in terms of the mathematical equations, we noticed that if L equals 0, there's no theta or phi in the functions. What that means is that we get a spherically symmetric orbital. And what's represented here is blue shading is equal to positive parts of the wave function, and yellow shading is equal to negative parts of the wave function. So in a 1s orbital, number one, you'll notice it's very small, right? So n tells us a lot about the size of the orbitals, and in a n equals 1 orbital is significantly smaller than an n equals 4 orbital. And one thing I'll also point out here is that these orbitals decay exponentially with regards to r. All of the r functions have this negative exponential behavior, but it depends on n how quickly they decay. And so what we're looking at is sort of the majority of the time the electron is in these spaces that we're looking at, but the actual function extends out further than what we're observing here, but the values get very, very, very small, and so we have to cut it off at some point. Okay, so our 1s orbital it's a ball. It's spherically symmetric, so there's no angular dependence, and that's true for all of our s orbitals, right? All of these have no angular dependence, which is why s orbitals look like spheres. One other thing you'll notice is that as n keeps increasing, we see multiple times where the function changes from positive to negative. So in a 1s orbital, we have 0 nodes, or areas where the wave function goes to 0. Whereas in a 2s orbital here, it's a little bit hard to see, but when it goes from blue in the middle to yellow on the outside, there's a spot where it goes to 0. And we get 2 of those in the 3s orbital, and 3 of those in a 4s orbital. Now we'll look at a different visualization that might make this a little bit clearer. All right, so those are known as radial nodes because they're nodes at a specific value of r. As we increase in L, as we look at p orbitals, so the 2s, 3p, 2p, 3p, and 4p in the second column, what you'll notice for all 3 of these is that we have an area in the middle for all 3 of them where we have a node that depends on the angle, and this is an angular node. So all of these, at least the specific p orbital shown here, all of them have an angular node that's horizontal. And so we have sort of a lobe of probability on top, a lobe of probability on the bottom, and a node in between where the wave function goes to 0. All right. And as we go down, so in the 3p orbital, we also have a radial nodes here and here. So we end up with 1 angular and 1 radial node. And again, we'll look at a different visualization of this to make this a little bit clearer. As we go to D, we see the same thing, where we get angular nodes here and here, as well as, and as we go down, we'll also get radial nodes. And you can see that, so the number of nodes corresponds to n and L. All right, and we'll go ahead and stop the video here.